Hey everyone, this is Philip. Today we're going to be going over the Unit 1 practice guide. This PDF can be found on Physics Guide. It can also be found on Dr. G's Classroom along with answer key, so you can reference that as well. Alright, let's jump straight into it. So question 1, if a car is traveling at a constant velocity, acceleration is 0, of 26 miles per hour, how much time does it take to travel 2,800 meters? So right away we get that our acceleration is 0. So we can write that off to the side here, 0 meters per second squared. And now let's take a look at the values that they give us. So we got 26 miles per hour, which is just a ratio. So we'll notice that miles per hour is not in our MKS units, which is the meters, kilograms, and seconds. So we're going to want to convert miles and hours to both meters and seconds. So we can go ahead and do that with conversion factors. There's around 1,600 meters in a mile. You can look up these conversions online as well. And in 1 hour, there is 3,600 seconds. So we can cross out hours, they cancel out, miles will also cancel out. And now if you multiply, divide everything out, you should be left with meters per second. You should get 11.6 meters per second there. And now, since our velocity is constant, we're going to look for an equation that has velocity in it. We're going to be looking for an equation that has time and displacement. So we do have one. It is going to be the delta x equal to initial velocity times time plus the 1/2 a multiplied by delta t squared. So since our acceleration is 0, if we plug it in here, this whole term is going to end up being 0. So we can just disregard that part of the equation for now and for the rest of the problem. So let's rewrite our simplified equation over here. So now we got displacement equaling the initial velocity times the time. So since the velocity is constant, that means the initial and final velocities will be the same because the velocity is the same everywhere. And so this velocity represents the velocity of the entire system. So we can just plug in the 26 miles per hour, which is equivalent to this here. We'll use this value here in for the v sub I. And then the delta t is what we're going to be solving for. And how much time does it take to travel 2,800 meters? So we'll plug that in there. And if you run a simple calculation, let me get out my calculator. So it looks like the delta t value will end up being 242 seconds. All right, question number 2. Isolate the expression for W. So go ahead and zoom in here. So we're going to be isolating the expression for W. So looking at the term as a whole here, it looks like there's a big square root over it. So immediately what we're going to do is square both sides. Sorry about the large pencil font here. Let me change that. So we're going to square both sides, which is going to leave us with L squared equals to 4t minus 5w. And now since we're isolating for w, we're going to try to keep this whole term to the right for now. So let's subtract 4t from both sides, which will leave us with L squared minus 4t equals negative 5w. And now we can go ahead and divide negative 5 by both sides. And that will leave us with the isolated expression for W. Question 3 asks us to graph a situation in which a cyclist travels 40 seconds and moves around on his bicycle. So we're going to be plotting a position versus time graph. In this case, the independent variable will be time, which is measured in seconds on the x-axis, and on the y-axis we'll have our dependent variable, which is the position in meters. So now if we read our statement here, first we can look at the position values. On this particular graph, we have 4 different segments here. And if we look at the highest position value, which is 120, we can divide that by 4 to kind of scale our x-axis. So 120 divided by 4 is 30. So I'm going to go ahead and label each of the increments here scales by 30. And for our time, we can just go ahead and label this 1, 2, 3, and 4 seconds. So now at 0 seconds, he's at position 0. At 1, he is at 30. At 2, he is at 90. At 3, he's at 120. And at 4, he's also at 120. So we can kind of connect the dots here. And now what this question is asking us is, during which time interval is he traveling the fastest? So in order to answer that question, we can kind of analyze the graph and see which segment of the graph, I plotted in red, has the largest slope increase. So which has the most position traveled in the shortest amount of time. So since this is the steepest segment of the graph here, it's going to have the highest slope, which means that he probably traveled the fastest during this segment here. And now which time interval is he traveling the slowest? Well, since there's a big plateau in the graph right here, during the 3 to 4 seconds, or multiplied by 10, 30 to 40 seconds, he's traveled 0 because he remains at the position of 120 meters. So he travels nothing during that time, which is the slowest, essentially. So question number 4 asks us to go ahead and do some simple conversion factors. So we'll go ahead and do those. So now 86 feet to centimeters. We want to find the conversion factor between feet and centimeters, maybe even meters if we can get that. This can be looked up online. You could have these in your notes as well. But some of these basic conversion factors are useful to know or memorize. So let's see. 86 feet to centimeters. So first we can try to get feet to meters. That works. So in 1 foot, there's around 0.305 meters. And to get from meters to centimeters, finally, we know that there are 100 centimeters in a meter. These units will cancel out, and the meters will cancel out. And if we multiply everything together, we should get around 2,623 centimeters. And now for this next one, millimeters squared to centimeters squared. We can think in terms of millimeters to centimeters. How many millimeters are in 1 centimeter? Well, in 1 centimeter, there are 10 millimeters. But since this is squared, we must also square this, so we can have millimeters squared on the bottom to cancel out this millimeters squared. And we'll also be left with centimeters squared, which is what it's asking for. So if we go ahead and do the math here, we will be left with 2.87 centimeters squared. And there you have it. And on question number 4, I did forget to mention that when you're squaring the millimeters squared, it'll also carry down to the 10, which will turn into 100. And that's why we divide 287 by 100 to get our answer. And now number 5. If a car has a velocity of 12 meters per second and speeds up to 31 meters per second in 167 meters, what is its acceleration? So we have three values that it gives us here. So it looks like it first has the velocity of 12 meters per second, which will be our initial velocity. This will, of course, be our final velocity, and this can be our displacement. And it's asking for the acceleration. So if we look at all our terms, we'll notice that we do not have a delta t. So we're looking for an equation that has these four terms in it. And luckily there is one. Final velocity squared equals to initial velocity squared plus 2a times the displacement. And we can just go ahead and plug everything in. We're solving for the delta or the a here. And it's just some basic algebra. Your acceleration should turn out to be 2.45 meters per second squared. Alright, moving on to question 6. This is one of those questions where you're going to have to identify these special cases. So an object falls 38 meters, our displacement, in 5.6 seconds, our delta t. What is our initial velocity? So what we're solving for here. So if you try to look for an equation with just these three terms, you might find that you're running out of luck. So what do? Well, we're going to need either a final velocity or an acceleration term to help us out. It looks like we don't have a final velocity, but we have an acceleration. If an object is falling, assuming this is on Earth, its acceleration is going to be negative 9.81 meters per second squared. Our g constant if you're taking any other classes that might deal with gravity. And we do have an acceleration. We do have an initial velocity, time, and displacement. And luckily there is an equation with those terms. And I'll go ahead and write that here. And if we go ahead and plug everything in, we go ahead and solve for our initial velocity here, do some algebra, we get that our initial velocity is 20.7 meters per second. Now the second part of this question, what is its final velocity? So we're solving for our final velocity. We already have a initial velocity that we solved for. We have the acceleration and we have the time. And we have an equation that deals with all of those terms in one. And just plug the values in for each term that we have. 5.6 seconds from this here. Do some algebra, some math, and you'll end up with negative 34.2 meters per second. And yes, in this case, our velocity is negative. And there you have it. That is the Unit 1 practice problem set.